Hello everyone, and welcome back. Today we're going to continue our exploration of foundational mathematics and focus in on one of the very important relations that we've discussed, and that is what is called linear relations. There are of course several other different types of relations such as quadratic, exponential, logarithmic, and trigonometric, and several many more, but linear relations are typically viewed as the most basic type of relations that have a variety of applications. So to start, what we're going to do is consider this following theorem that says the following. If you have 2 points, say P1 and P2, inside of a plane, then there is a unique line that passes through both of these points. So if we were to have these points P1 and P2, for which I have graphed here, and I were to ask you, draw a line through these 2 points. Generally speaking, it doesn't matter who I ask, as long as you have some intuition of what a line is, everyone will draw the same exact line, in particular this line here, L, which I'm going to be exploring in terms of properties. Now one could ask, well, what exactly is a line? And one could define a line as a geometric object that has this particular slope. That is, it has the same rate of increase or the same rate of decrease or no increase at all as you progress along, for example, the x and or y domain. And that would be a sufficient definition, but we'll give an algebraic definition of what it means to be a linear relation a little bit later. So let's just work with just a vague definition of a linear relation, and it's one that falls in the xy plane that has this quote-unquote linear graph. So a couple basic calculation things that you definitely should be able to do before we get into the more sophisticated applications of lines. The first of them will be the length of a line segment. So the length of a line segment, which is sometimes also viewed from the perspective as the distance between 2 points. So what I'm going to do is I'm going to consider 2 points in the xy plane, so horizontal x, vertical y. Let's assume that I have point 1 here and point 2 here. So since they're both located in the xy plane, that means they have an x value associated to each of them and a y value associated to each one of them. So let's assume that, for example, point 1 has the x and y values x1 and y1, and let's assume that p2 has the x and y values x2 and y2. Here x1, y1, x2, y2 are all real numbers, let's assume. So if they're all real numbers, that means there exists some position on each of these, for example x1 and x2, on the y-axis, y1 and y2. And I could ask, well, what is the distance, or the shortest distance rather, between these 2 points, P1 and P2? So what I'm actually going to do is I'm going to draw a horizontal line from x1 to x2, but along the line y is equal to y1, and I'm going to put a point there, and I'm going to draw a vertical line here. So as you should already know from basic geometry, a horizontal and a vertical line are always perpendicular to one another, so the angle between these two orange lines is going to be 90 degrees. So if those line segments form a 90-degree angle, that means the blue length would be the length of the hypotenuse of the associated right triangle. So as we should already know, let's assume that we're going to name the hypotenuse length D. And what would be the individual lengths of this triangle? Well, the distance between x1 and x2 would just be x2 minus x1. The distance between y1 and y2 would just be y2 minus y1. So by the Pythagorean theorem, what do we have? So Pythagorean theorem, a squared plus b squared plus c squared, as people often say, will be the following. In particular, d squared, which is going to be the c squared in the a squared plus b squared relation, is going to be equal to the length, which is x2 minus x1, the quantity squared, plus the height, which is y2 minus y1 squared. So that's our a squared plus b squared is equal to c squared relationship, which is coming from the Pythagorean theorem. Now keep in mind, what we're interested in is d, not d squared. So what I'm going to do is I'm just going to take the principal square root of both of these things, and we're just going to be left with d on the left-hand side. So we have that the distance between points A and B is just going to be equal to the square root of x2 minus x1, the quantity squared. Some people call x2 minus x1 the increment of x. And then we're going to have y2 minus y1, the quantity squared, which some people call the increment of y squared. Another important representation between 2 points of a line is what we call the midpoint. So in this particular picture, if we have x1 here and x2 there, and y1 here and y2 there in terms of the horizontal and vertical components, then what we call the midpoint is the point that is sort of in the middle of P1 and P2, such that the distance between P1 and the midpoint is the same as the distance between the midpoint and P2. So obviously the midpoint is also going to be a point, not a number, so you should have an x value and a y value associated to it. And you should be able to see that, for example, the x value of the midpoint is just going to be the average of x1 and x2, and the y value for the midpoint is just going to be the average of y1 and y2. So what we call the midpoint between P1 and P2. So the midpoint between P1 and P2 is given by the following relation. So the midpoint between P1 and P2 is going to be equal to another point. So it's going to be x1 plus x2 divided by 2. The average of the x values will give you the x value for the midpoint, and the average of the y values, y1 plus y2 divided by 2, will give you the a y value associated to the midpoint. Another common relation between 2 points is what we refer to as the slope. Some people also use the word gradient of the line, or the line segment, depending on what object you're actually looking at here. So the slope or the gradient of a line. So let's bring our little picture back. So our goal is to find the slope or the gradient of this line. And what exactly do we mean by slope? Let's assume this is x and this is y. So the slope or gradient tells you about the steepness of that particular line. So for example, this red line is more steep in the positive direction compared to, for example, this pink line. And for example, you could have a steepness in the negative direction. For example, this green line is not as steep as this orange line as it goes down. And typically when we talk about steepness, we usually are referring to the steepness as we move from left to right on the x-axis. So the slope between these 2 points, so the slope, which we usually represent by a lowercase m, is going to be equal to, and you may remember this formula, is going to be y2 minus y1, so the increment of y divided by x2 minus x1. And some people will often remember this to avoid getting these mixed up as rise over run. So rise the y value, run the x value. But it's the change in y divided by the change in x, and it's very important that you have these indices 2, 2, and 1, 1 matching each other. Also, you could do y1 minus y2 over x1 minus x2. That will give you the same exact answer, but the indices have to line up in terms of the columns. So those are 3 basic metrics associated to 2 points in a plane, in particular the distance, the midpoint, and the slope. So let's actually go through a quick calculation example of how you would do this on paper, just in case you need a little bit of practice. So let's assume we have the point A, which is the point -3, 5, and let's assume we have the point B, which is the point 0.76. And let's find the distance, midpoint, and slope between these 2 points. So the distance between A and B is going to be equal to what? So that's going to be the square root of, and we can label these, for example, x1, y1, x2, and y2. So it's going to be the square root of x2 minus x1, so x2 minus x1 squared plus y2 minus y1, the quantity squared. Now notice that 7 minus -3 is the same as 7 plus 3, so that's going to give us 7 plus 3, which is going to be equal to 10 squared, and then 6 minus 5, that's going to be equal to 1 squared. So we have the square root of 100 plus 1, which is the square root of 101, which we can find to be approximately equal to 10.05. So that's the distance between these 2 points. So now let us find the midpoint between A and B. So that's going to be equal to x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. So negative 3 plus 7 is the same as 7 minus 3, which is going to be equal to 4 divided by 2. 5 plus 6 is going to be equal to 11 divided by 2. And as decimals, we have that that's going to be equal to 2, and that's going to be equal to 5.5. So that is the midpoint between those 2 points. And now let's do the slope between these 2 points, and you could write m or MAB, it doesn't really matter. So that's going to be equal to what? So that's going to be equal to y2 minus y1 all over x2 minus x1. So the change in y divided by the change in x. So that's going to be equal to 1 over 10, or as a decimal, 0.1. So how do you interpret this slope? So is this line increasing, decreasing, or is it constant? So it's very important to know and being able to interpret each of these things. So this is what we refer to as an increasing line, a decreasing line, and a constant line. So that would be our constant function from before. So we say that a line is increasing if the slope of the line between any 2 points on that line is going to be positive. Now it's very important to notice that regardless of the 2 points we choose on a line, the slope is always going to be the same. Also, if we choose 2 points on a what we call decreasing line, then the slope is going to be negative. And if we choose 2 points on a constant line, then the slope is going to be equal to 0. And I actually want to mention that point that I just made just a moment ago. And it says this: regardless of the 2 points chosen on a linear relation, the slope will be the same, which some people will take as the definition of a line. But that's how you can calculate the distance, midpoint, and slope given any 2 points. Now that we know how to do a couple basic calculations on linear relations, now let us see if we can quantify linear relations in a set theoretic manner. In particular, can we find the equation of a line for which all points on that line satisfy? So consider the following statement. Suppose that L passes through points x1, y1, and x2, y2. Then, if L truly is a linear relation, then there exist real numbers a, b, and c with the restriction that a and b are not both 0, such that ax plus by equals c represents all points xy in the R2 plane that belong to that particular linear relation, including these points x1, y1, and x2, y2 mentioned above. Now, let's look at a couple special cases of this linear relation ax plus by equals c. Keep in mind a and b both cannot be equal to 0, but individual values a or b could be 0. So let's take a look at that. Well, so let's assume that a, for example, is equal to 0 with b not being equal to 0. So that gives us what? So a is equal to 0, so we have 0 times x plus b times y is equal to c. So 0 times x is going to be equal to 0 regardless of what x is. So we're going to have by is equal to c. Keep in mind b and c are both numbers, but y is a variable. So we're going to have y is equal to c divided by b. Keep in mind c and b are both real numbers with b not being equal to 0. Therefore, this should look very familiar. This is our constant function, which is sometimes viewed as a horizontal line. Right, so horizontal lines are linear relations for which the a constant in the general form of the equation is equal to 0, giving us y is equal to some constant form. So if we consider the other case, for example, a not equal to 0 and b being equal to 0, what does that give us? Well, that's going to give us ax plus 0 times y is equal to c. And that gives us what? Ax is equal to c. And since a is not equal to 0, we can divide both sides by it. So we're going to have x is equal to c over a, which is also a constant function, but it's a constant function with respect to the other variable. So if y is equal to a horizontal line, then that means x must be a vertical line, right? But that's, of course, not a function, right? So we typically do not consider vertical lines, right? But they do exist nonetheless. So those are the two special cases, horizontal and vertical lines. So now let us assume that A is not equal to 0 and B does not equal to 0, which you can put in one statement, A times B is not equal to 0. So if that is the case, then what do we get? So we have AX plus BY is equal to C. And what I want to do, since we're going to be primarily focused on functions, is I want to solve this equation for y. So I'm going to move the AX to the right-hand side. So I'm going to have that BY is equal to minus AX plus C. And since B is not equal to 0, I'm going to divide both sides by it. So then I'm going to have what? So I'm going to have y is equal to minus a over b times x plus c divided by b. And since a and b and c are all real numbers, I'm just going to call this real number capital A and I'm going to call this real number capital B. So then I have an alternate form, y is equal to ax plus b. So this is the representation of all linear relations that are functions. So if a linear relation is a function, then there exist these real numbers a and b such that y is equal to ax plus b. Now, one can ask, well, what is so special about linear functions? And is there any special meaning behind these numbers capital A and capital B? So let's first off recall that x1, y1, and x2, y2 both satisfy this particular linear relation. That means that y1 must be equal to a times x1 plus b, and also y2 is going to be equal to a times x2 plus b. So since both of these are going to be true, I can also subtract these equations and I'm also going to get a true relation. In particular, y1 minus y2 is going to be equal to ax1 minus ax2 plus b minus b. So once I have that, notice that the b minus b does cancel out, and I'm just going to be left with y1 minus y2 is equal to, and notice a is in common with the right-hand side, so I can factor that out of the left, for example, and I'm just going to be left with x1 minus x2. So what I'm going to do is I'm going to divide both sides by x1 minus x2, so x1 minus x2, and I'm going to have what a is equal to. So I have that a is equal to y1 minus y2 all over x1 minus x2, which keep in mind is equivalent to doing y2 minus y1 over x2 minus x1. And what is so special about this little formula? This is the slope of the line that passes through them. Right, so that's very interesting, but we do have a requirement that x1 cannot be equal to x2 because if x1 and x2 were equal to each other, that means they fall on a vertical line and hence it is not a function, provided that y1 and y2 are of course different. Right, so there is obvious geometric meaning associated to capital letter A in this equation y is equal to ax plus b. Now, what is so special about the other constant, in particular capital B? One notice that when x is equal to 0, y is equal to capital B in this particular relation. And remember, when x is equal to 0 and a line crosses a point at that value, this is what we refer to as the y-intercept of the linear relation L, assuming that x is on the horizontal and y is on the vertical axis, which is typically the standard. So what we have here for the equation ax plus b, we actually have very important meanings for this linear function. Right? So if a linear relation is a function, then there exists these capital numbers a and b, such that a represents the slope and b represents the y-intercept of the line, and we usually refer to this equation as the slope-intercept form of the linear relation, and we refer to the other one, which is often represented as ax plus by is equal to c, as the general form of the linear relation. Because keep in mind, the general form can take the form that are not functions, in particular vertical lines, but a linear function cannot take vertical lines as possible outcomes of chosen numbers, capital A and capital B. So now that we have the basic understanding of what this capital A and capital B is, let's actually work through an example and see how to find them. If we were given 2 points and we want to find the equation of the linear function that passes through both of them. So let's assume that we have the points, for example, -3, 5, and 7, -4. So we already know that the slope is one of the important things that we have to find, and we know how to find the slope between 2 points. So let's just go ahead and start with that. So we're going to have y2 minus y1 all over x2 minus x1. So that's going to be -4 minus 5, which is -9, over 7 minus -3, which is 7 plus 3, which is going to be equal to 10. And of course, we can write that as a decimal if we want as -0.9. The next thing that we need to find is the value of b, because keep in mind, we know that the equation is going to be equal to y is equal to -9/10 x plus some number b. We just need to figure out what exactly is this number equal to. So keep in mind, both of these points must fall in this line, so we can choose any of these points to figure out what b actually is equal to. So what I'm actually going to choose is this first number, because since x is negative in the first point, it's going to make that term positive, and I like working with positive numbers, so I'm going to just go ahead and choose that one. But if you choose the second point, you should be confident in yourself that you will get the same exact answer. So if I choose the point -3, 5, so -3 is x and 5 is going to be our y value, then I'm going to have 5 is equal to -9/10 times -3 plus that y-intercept number that we're trying to find. So that's going to give us 5 is equal to -9 times -3. That's going to be positive 27 divided by 10, plus that unknown number b. Subtract 27 tenths from both sides, so we're going to have b is equal to 5 minus 27 tenths. And we need a common denominator, so we need to multiply top and bottom by 10. So that's going to be equal to 50 divided by 10 minus 27 divided by 10, and that's going to be equal to 23 divided by 10, which is 2.3 as a decimal. Therefore, the equation of the line that passes through these 2 points is going to be equal to y is equal to -9/10 x plus 23 tenths, or you can write this as a decimal as y is equal to -0.9 x plus 2.3. Either one will give you the same exact output values. Now, of course, that's the slope-intercept representation, but we could go for the general equation because sometimes that might be more useful than the slope-intercept equation. So I'm going to be working with the fractional form because I think the fractional form is a little bit more easier to get the general form out. And what I'm going to do is I'm going to multiply both sides of this equation by 10 to get rid of those fractions. So once I do that, that's going to give us 10y is equal to -9x plus 23, and I'm going to shift my 9x to the left-hand side. So it's going to give us 9x plus 10y is going to be equal to 23, and that's our ax plus by is equal to c form. Now, of course, we could scale both sides of this equation down by 3, multiply both sides by 2, we can negate both sides. There's infinitely many ways you could represent this general form, but since 9, 10, and 23 are all relatively prime, this appears, at least to me, to be probably the most ideal representation for the general equation form of this line. Let's consider the following example, in particular these two linear relations. So let's assume that L1 is the relation consisting of points x, y that satisfy this particular equation, and L2 is the set of all xy points in 2 dimensions that satisfy this particular relation. So they are going to be generating 2 lines in the xy plane. So the question here is, where does the line 1 and line 2 cross one another? So if you think about this geometrically, assuming that they don't have, for example, the same slope or they are the same exact line, they should be crossing somewhere. Now there are 2 other cases that you need to keep in the back of your mind. For example, it's possible that these lines do not cross, and it's also possible that they are actually the same exact line sitting on top of each other. But of course the question is posed is if they do cross, so we're going to be looking for this point x comma y for which these 2 points these 2 relations actually have in common. So the point of intersection xy must belong to L1, and this point of intersection xy must belong to L2. In particular, the intersection of these 2 relations must be only the point xy, right? So we need to find this point xy. That makes it true. So let's actually look a little bit more detail at this first relation because this definitely looks a little bit messy, especially with all the fractions. So let's look at linear relation 1. So what we're going to do is we're going to distribute this 1/2 into the x and into the 1/2. That's going to give us 1/2 x minus 1/2 plus 3/4. And then I'm going to get a common denominator. I'm going to multiply that by 2. And that's going to give us 1/2 x minus 2/4 plus 3/4. And that's going to give us 3/4 minus 2/4, which is 1/4. So the first linear relation can also be written as y is equal to 1/2 x plus 1/4. And we're actually going to be working with that because it's a little bit more nicer. Similarly, let's look at linear relation 2, and what we're going to do is we're going to distribute this 5/6 to this x and that negative 5/6 to that negative 2. That's going to give us minus 5/6 x plus 10/6, and then we have that lonely plus 1, and of course we're going to multiply top and bottom of that by 6, and that's going to give us minus 5/6 x plus 10/6 plus 6/6, and 10 plus 6 is of course going to be equal to 16, so we have L2, which is going to be y is equal to minus 5/6 x plus 16/6, which is actually the same thing as 4. Well, not 4 exactly, but it's going to be minus 5/6 x plus 8 divided by 3. That's what it reduces to. So we're going to be working with this particular relation for linear relation 2 because it's a little bit more easier to work with. So if these two lines cross, then these values of y must be equal to each other. So if the y of the first equals the y of the second, then this implies the 1/2 x plus 1/4 must be equal to minus 5/6 x plus 8/3. Right? So what I'm going to do to solve this linear equation is I'm going to multiply both sides by the least common multiple of 2, 4, 6, and 3. So what is the least number that 2, 4, 6, and 3 all divide into? You should know that that is going to be equal to 12. So I'm going to multiply both sides of this equation by 12, and that's going to give us what? So 12 divided by 2 is going to give us 6. 12 divided by 4 is going to give us 3. 12 divided by 6 is going to give us negative 2 times 5 is going to be negative 10. And 12 divided by 3 is going to be 4. And 4 times 8 is going to be equal to 32. Right? So once we have this, what do we have? So now I'm going to isolate my variables to the left and to the right. So I'm going to add 10x to both sides. I'm going to subtract 3 from both sides. So I'm going to have 16x is going to be equal to 32 minus 3, so that's going to be equal to 29. So the value x for which they have in common is going to be equal to 29/16. So now we know the value of x that is satisfied. Now we need to find the value of y. Keep in mind they have the same exact y value, so we can either use L1 or L2. I'm going to use the equation for L1. So the y value is going to be equal to 1/2 x plus 1/4, and then we're going to evaluate this at this particular x value. So that's going to be equal to, once we evaluate, 1/2 of 29/16 plus 1/4. So that's going to be equal to 29 divided by 32 plus 1 over 4. And then I can multiply, for example, top and bottom by 8, and that gives me a common denominator of 32. So I have 29 plus 8, which is going to be equal to 37, all divided by 32. So that's my common value of y. That means my point of intersection for L1 and L2 is the point 29/16, comma 37/32. So that's how you can find the point of intersection for two lines if they do have a unique point of intersection. So we've already pointed out that if you have a linear relation that is indeed a function of x, then there do exist these numbers a and b such that f of x is equal to ax plus b, and we've already shown that a represents the slope of any 2 points on that line, and b represents the y-intercept of that line. So what would be the domain of this particular linear function? So you should know that the largest possible domain that I can choose for this is going to be the set of real numbers, or you could choose the domain to mean any subset thereof. But if this is the domain for which you choose, then what would be the associated range for this linear function? So keep in mind the range is going to be the set of all real numbers, provided that the slope is not equal to 0. If the slope is not equal to 0, that means it's always going to increase from minus infinity to infinity, or it's going to always decrease from positive infinity down to negative infinity. But if the slope is equal to 0, that means it's going to be a constant function, and it's only going to be equal to the number b for all x values for which you input. Now, another question that I want to ask is, do two linear relations always intersect? You should, of course, already know the answer to this, and you should say the answer is no, they don't always intersect. So under what conditions do two linear relations, for example, let's assume we have one linear relation, f of x is equal to a1x. Actually, let's call it m1x because we actually know that that's the slope of the first line, and b1 for the intercept. Let's consider another linear relation, g of x, which is equal to m2x plus b2, the slope and the intercept of the second linear relation. So if f of x is equal to g, then what would that imply? So if f of x is equal to g, that means they equal each other at some particular y value, right? So we want to find a condition on m1, m2, b1, and b2 such that the solution to this equation always exists. So if f of x is equal to g of x, then that means m1x plus b1 is equal to m2x plus b2. So if these two y values are indeed equal to each other, what must x be equal to, or what must b and m satisfy? So what I can do is I can move my x term to the left-hand side, and I can move my my b term to the right-hand side via subtraction. So that's going to give me m1x minus m2x must be equal to b2 minus b1. And I can factor out an x out of the left-hand side, and that's going to give me x times m1 minus m2 is going to be equal to b2 minus b1. And then I can divide both sides by this quantity here, and that's going to give us x is equal to b2 minus b1 divided by m1 minus m2. So if these two y values, y1 and y2, are equal to each other, then the x value for which these lines do cross is located at this point, and this exists and is unique if m1 does not equal to m2. Right? So if m1 does not equal to m2, then the denominator cannot be equal to 0, which is a good thing because you can't divide by 0. But that gives us a requirement for there to be at least a intersection. It could be infinitely many, actually. It exists, actually, I don't want to say and is unique, but it exists if m1 and m2 are not equal to each other. That's an obvious truth. Now, what are the other cases? Because what if B2 and B1 are equal and M1 and M2 are equal? Like, that's a possible scenario. So the scenario that we have in case B1 and B2 are not equal to each other are going to be these two lines here, for example, line 1 and line 2. So this is the case where slope 1 and slope 2 are equal to each other, and the intercepts B1 and B2 are not equal to each other. If these two criteria are met, then we call these two lines parallel lines. So these are what we refer to as parallel lines. Right? So that's one scenario, and let's look at the other scenario. So let's assume that, for example, M1 and M2 are equal, and B1 and B2 are both equal. So we have a 0 divided by 0 scenario for that x. So if that is the scenario that we have, then line 1 and line 2 are actually the same exact line. In this case, we call these lines collinear lines. Collinear, i.e. they are practically codependent on each other, i.e. they are the same exact line. And another scenario that we've already explored is if these two lines are not equal to each other. They could have the same y-intercept, they could not, doesn't really matter. They're going to cross eventually. So this is the case where m1 and m2 are not equal to each other. So these are what we refer to as intersecting lines. So intersecting lines. intersecting lines that are not collinear in particular. So if they do intersect one another, then there's going to be some angle, say theta, between these two lines, right? So there will be some angle between the lines. You could either focus on that angle there, or you could focus on this angle there. It doesn't really matter which angle you look at, but there's going to be some angle between them. Now, if the line, or if the two lines do cross at a special angle, so in particular, if they cross in this fashion where this angle is actually 90 degrees, so if that angle is 90 degrees, then we refer to these two lines as perpendicular lines. So perpendicular lines. And one can show that if two lines are perpendicular, then the slope of one is equal to the negative reciprocal of the other. I'm not going to prove that here, but one could do a basic geometric proof, although algebraically intensive, that this is the case. So for example, let us assume we have, for example, y1, which is equal to like 3/4 x plus 5/8, and let's assume that we want to give a line that is perpendicular to that. So the slope of a line perpendicular to this particular line y1 is going to be equal to the negative reciprocal of the slope of this line, which is going to be equal to -4/3. And somebody could give you a point for which this perpendicular line passes through, and you could find the y-intercept of that line if you desire. But those are all of the primary and fundamental things that you definitely should know when it comes to linear relations, and in the next video we'll talk about some applications that are actually commonly used with linear relations and linear functions. So I hope you enjoyed, and I'll see you in the next video. Take care.